Good afternoon to all of you and welcome back to the 18th lecture of STAR 2026. Today's first lecture is on Detectors and Sensors by Srivastava, Space Application Center, ISRO, Ahmedabad. We welcome Sri Nidesh to STAR 2026 session. Moderator of this session is Mr. Hriday Patel from the same center, that is Space Application Center, ISRO, Ahmedabad. Mr. Hriday completed BTech in Electronics and Communication Engineering from LD Engineering College, Ahmedabad. He has been working as Electro-Optical Payload System Engineer at Space Application Center since the last 6 years. May I welcome Mr. Hriday to moderate this session. Over to Mr. Hriday.
Thank you, sir, for giving me opportunity to introduce Nitesh, sir. He's received his BTech degree in ECE from Uttarakhand Technical University, Dehradun, India. He joined the Space Application Center, Indian Space Research Organization, Ahmedabad, India in September 2010 and has been working there since then in system design, development, testing and characterization of spaceborne imaging system. He received ISRO's Young Scientist Merit Award in 2015 and Team Excellence Award in 2016 and 2018. Currently, he is working as a team lead for MUX multispectral payload of India Mauritius joint satellite and associate project director for microsat 2AR1 and 2BR1 payload. Now, I kindly request Nitesh sir to present related to detector.
Thank you, Hide, for your kind words. So I'll start with the presentation. I'll just share my screen. So hope my screen is visible.
Yes.
So good afternoon, everybody. So I'm Nitesh Thapa. I'll be talking about detectors and sensors for optical remote sensing today. So before we begin, let us understand what a detector or a sensor means. So if you look at it, the detector or sensor is a very broad term as it applies to many fields. However, if we see in general terms, we can say that a detector is a device that responds to a physical stimulus or a signal and produces an output that represents the stimulus that it has measured. So essentially, it is a transducer that converts one form of energy or signal into another. The input signal can be physical signal like force, pressure. It could be electrical, it could be temperature, or it could be light, which is in our case. So in field of optical remote sensing, a detector or sensor converts the electromagnetic radiation or light as we generally call it into an electrical signal which can then be further processed and recorded for further interpretation. So these are the points that I'll cover in my talk today. First of all, why detectors are required. What's the principle of detection behind the operation of such detectors? What are the major characteristics of detectors and how we choose upon the detectors for our applications? What are the various types of detectors and the detectors that we have been using in ISRO? So now the first topic, which is why our detectors are required. So this is basically, if you look at the remote sensing overall domain, so remote sensing is a process of acquiring information about an object or an area without coming in the physical contact with it. So essentially, it is observing something from a distance. Okay. Now, if you look at in this picture, sun is acting as an energy source. So it is the primary energy source for us. So it illuminates the Earth's surface. If you look at the Earth's surface, it can comprise of forest, building, water, and various targets. So when the sunlight hits an object, some of the light gets absorbed, some is transmitted, and some is reflected back. Now, the amount and the wavelength of the reflected signal or reflected light depends upon the object physical and chemical properties. Now, the key point over here is the sensor, which is sitting on the satellite. Now, this sensor detects the reflected sunlight Now the sensor typically have multiple bands which caters to different electromagnetic region, and each sensitive to the different wavelengths. Now this further goes to the ground station where the digital image is created for various bands, which is then further converted into user applications. Now the applications can be weather monitoring, it can be disaster management, or it can be a simple map making application. Now this is the electromagnetic spectrum we generally know of. So here it shows range for the electromagnetic radiation, the radiation that travels in waves. Okay, so it is how the energy is moving through the space. Now, in optical remote sensing, we generally deal with the signal ranging in the UV, which is highlighted over here, which is typically 0.01 micron to 0.4 micron, and the visible light that we generally see, which is 0.4 to 0.68 to 0.7 micron, and then infrared. Infrared is the wavelength which is higher than red wavelength. It is not, we cannot see this light, but this plays a very critical role when it comes to remote sensing. So on the right hand side, you can see the wavelengths that we generally deal with. The UV as we talked about, then visible, then the IR, the infrared is further bifurcated into various wavelength regions. The definition could vary from sources to sources. However, typically we say that beyond red, 0.7 to 1.5 is near infrared. Then we have short wave infrared, we have mid wave infrared, we have long wave or thermal infrared, and then far infrared, which can be as high as 1 mm wavelength. Now, this is how the Earth appears in different wavelengths. So this gives us an insight that we need to operate our sensor in different wavelength regions to get different information about the target, which primarily for us is Earth. Now, this is the complete optical imaging system. So we have the incoming light, as we discussed in the earlier slide. The incoming light is coming from a target, which carries the information about the target. The first element it encounters in an optics, which essentially transforms the incoming beam and focuses it into a detector. Now, as we discussed, that there's a wide range of EM spectrum that may be falling on the detector. To further narrow down on the spectrum, we use a spectral selection system. It could be a simple filter like red, green, and blue, or it can be a complex system as well. Now, the detector sits at the heart of the system, where it converts the optical energy suitably filtered by the filter into the electronic signal. And this whole system is housed in a mechanical assembly. So we can see that one of the most critical component over here is detector, because that's where the energy conversion from optical or from electromagnetic radiation to electronics happen. Now, the second point of our talk is the principle of detection. Now, if we talk about detectors, so based on the detection principle, they are classified majorly into thermal detectors and photon detectors. What do you mean by thermal and what do you mean by photon? We'll try to explain this. So as the name suggests, thermal detectors sense the radiation that is by absorbing the power and causing change in its physical properties. The physical properties could be its rise in temperature, its electrical properties, or some other. And the examples are thermocouples, thermobiles, and borometers. We'll talk about them separately. However, the thermal effects do not depend upon the photonic nature. So it does not care that which photon it is, which photon is incident on it. It is basically depending upon the heating effect of the infrared radiation it is sensing. So generally speaking, it is a broadband. So it can cover to a larger EM spectrum. But however, since it is based on the heating property, the response time is generally slow. Because when heating, you have to raise the temperature to the equilibrium, which will take some time. So it has a higher time constant. Now coming to photon detectors, here that light to charge conversion happens by interaction of the incidence radiation in terms of photons. Okay, and the detectors are made up of generally semiconductors, various class of semiconductors. And since they are responding to photons, there's a term called band gap that we'll discuss subsequently. Only the photons which have energy more than the band gap will be able to sense. So they become spectrally selective. However, since they are working on partition of photons, they are very fast. They can respond in microseconds. Now coming to detail of thermal detectors, on the left side we can see a thermocouple or multiple thermocouples put together, which is generally called a thermopile, series of thermocouples. It's a simple, rugged and a versatile temperature sensor. And the principle is based on Seebeck effect. That is, when two dissimilar metal wires are joined at both the ends and one of the junction is heated, a voltage is created. You would have heard about the Peltier effect, which is reverse of this. So here the heating is carried out by foreign radiation of the, and the voltage is directly related to the temperature difference between the two junction, and thus indirectly it is proportional to the radiation intensity. So essentially the heat energy is converted into electrical energy. And as we already discussed, the thermocouples are less sensitive, so we need to put multiple of them together in order to make it sensitive. Now on the center, I've shown pyroelectric materials. So there are certain materials like lithium tantalate, lithium niobate. They are called pyroelectric materials. They exhibit a spontaneous electric polarization that is temperature dependent. This means that when the temperature of the material changes, its electrical polarization also changes, which generates an electric charge. So unlike the other IR detectors, which are sensitive to the continuously falling radiation, pyroelectric detectors essentially measures the rate of change of the energy. Now on the right hand side is the bolometer, and this is the most common used thermal detector. These are essentially thermal detectors which measure the electromagnetic radiation across the wide spectrum. Actually, from visible to infrared and even in some cases some millimeter waves. And unlike pyroelectric detectors, it measures the actual temperature. So a key component of this bolometer is the absorber, which is seen on the top. This is the material which actually absorbs the energy. And below that is a component which need to have a thermal mass of which the temperature changes. And this, the absorber must be thermally isolated from its surroundings so that its temperature increases only due to the falling radiation. Now coming to the photon detectors, the very principle that defines the operation of photonic detectors is photoelectric effect. So it's a fundamental phenomena in physics that demonstrates the quantum nature of light. So it was discovered in 1887 by the German physicist Henrik Rutherford. What he observed was that electric charged particles are released from and within a material when it absorbs electromagnetic radiation. It was also observed that the light with only certain wavelengths were able to produce the phenomena. The energy of the particle also was near constant for a fixed wavelength. So even if you increase the intensity essentially means the number of photons of a lower wavelength, of a higher wavelength, it was not able to produce any free component. So further, Einstein provided the theoretical explanation for this, for which he earned the Nobel Prize. He proposed that the light isn't just a wave, but also exists as a discrete packet of energy called photons. And this is what is interacting with the surface. So if the photons energy, which is generally defined as hf or hc by lambda, where h is the Planck's constant, c is the speed of light, lambda is the wavelength, or f is the frequency, it can be used interchangeably. So whenever the photon has energy, which is given as hf, more than the work function of a metal, then only the electron can be set free. And the kinetic energy of the electron, which is setting free, will be the difference of the energy of the incoming beam to the work function. So this basically is the fundamental theory which form the basis of photon detectors. Now coming to photoconductivity, it's a phenomena where the electrical conductivity of the material increases when it's exposed to electromagnetic radiation. It is very closely related to photoelectric effect, but instead of emitting electrons from the surface, the light liberates existing electrons within the material, so allowing them to contribute to the electric current. So this diagram shows a band gap diagram. So we'll take a minute or so to explain this. So generally, this is the Fermi level, which is shown over here in dotted line, is the energy level at which there is a 50% probability of finding an electron at any given temperature. Okay. So now if we look at metals, which are essentially generally semiconductors, so the Fermi level lies within the conduction band. This means that there are plenty of available energy states just above the Fermi level, allowing electrons to freely move and conduct electricity very easily. And there is no band gap to overcome, and thus the metals, their conductivity does not change very much with the light incident on them. Now, on the extreme right side, if you look at the insulators, the Fermi level is almost in between the conduction band, which is on the bottom, to the valence band at the bottom to the conduction band at the top, and the gap is very high that there are very few to none electrons in the conduction band, and it takes huge amount of energy to excite an electron from the valence band to conduction band in order to make it conductive. Now, semiconductors lies in between them, and we can call them as a sweet spot. So this is where the Fermi level gets very interesting. So in intrinsic, if you look at the Fermi level is near to the mid of valence and conduction band. And however, if we dope by p-type or by n-type, the Fermi level can be suitably modified. So if you look at semiconductors, the electrons are bound within the atoms. They are not free to move. However, if a photon of sufficient energy impinges on it, they are liberated and they generate a free electron hole pair. So the phenomena goes like this. When a photon with sufficient energy is absorbed by the material, there's an electron hole pair generation. Okay, so the electron will be liberated from the valence band and it will go to conduction band. While going up, it will leave a hole behind in the valence band, which will also add to conductivity, and then free electron in the conduction band, which will also lead to conductivity. So depending upon the falling radiation, the conductivity of the semiconductor changes. So there are various materials like silicon, germanium, cadmium sulfide, they have moderate band gap, and visible light is able to excite them. Now coming to photovoltaic effect. If you look at the photovoltaic effect, it lets a semiconductor convert sunlight into a usable energy. However, this is the principle that powers the solar panels and many other light to energy application. However, for us, it is essentially a generation of an electron hole pair, which can then further be measured in order to get the estimation of the falling light. Now, looking at the detector materials, now as already discussed, the band gap of the material and the electromagnetic radiation that we want to study are very closely related. On the right hand graph, you can see the wavelength versus the band gap relationship. So higher the wavelength, it can only excite an electron of a very narrow band gap. However, if we want to measure wavelength which is lower, we need to have a higher band gap. So the choice of material depends upon the wavelength of interest. And generally speaking, silicon is the most preferred material for visible bands, and MCT is the most common material for IR wavelength. So these are the various materials that we use, like panchromatic film, the film we used earlier in photography. So it has a broad spectrum from UV to NIR, and it caters to the visible band which we are used to, the human eye. Then infrared film was further enhanced towards NIR. Lead sulfide is a choice when we are going up to MIR, and then indium antimonide. MCT is a very broad band device which can be further tuned based on the composition ratios of mercury telluride and cadmium telluride. And then we have thermistor and pyroelectric sensors as well. Now coming to characteristics of the detectors. Now, based on size of the detectors, they can be classified as either single element or a linear device or an area array device. So as the name itself suggests, single element has only a single pixel. So pixel is the smallest element of detector. Whereas in linear, we have lines of detectors and they form a one-dimension array. However, in area array, which is generally there in our cell phone cameras, it is able to capture a two-dimension image. It has two-dimension m cross n array. So this is how an area array is actually, and it has m cross n, and you may be familiar with the term megapixel. So it is basically product of m cross n. Now coming to the various sensor parameters. The first sensor parameters for specifically for photon sensors is the fuel capacity. So we discussed that the incoming photons is converted into free electrons. Now these free electrons, in order to be sensed, they have to be captured and collected. So a device which can collect more and more electron is known to have a higher full well capacity. So by capturing more and more electron, we'll be able to improve our signal and thus the signal to noise ratio. The second parameter is the resolution. We'll have slide on this as well. Essentially, it is a difference of having a 1 megapixel camera versus a 10 megapixel camera. The more numbers of pixel you have, you may be able to differentiate between smaller targets. Then comes the fill factor. So fill factor is defined as the area of the physical area of the pixel versus the area where it is sensitive. So generally in photon detectors, if we have an associated electronics with it, some of the area may not be responsive to light. But in order to improve the signal, we would try to maximize the fill factor. Then comes the quantum efficiency. Quantum efficiency is the efficiency of the detector to convert the incoming photons into electrons. It is essentially the ratio of the generated electrons versus the incoming photons. I have a slide on that as well. Then comes the dark current. So generally, as we said, that these detectors, the band gap is sufficiently broad that they do not respond, they do not uh, generate current when it is dormant. Only when light is falling into it, they should be able to conduct. However, due to some thermal phenomena, the dark current exists. So even when there is no light falling into it, there will be some response from the detectors. And generally speaking, dark current we would like to minimize. Then comes the read noise. Now we have collected the electrons, but these electrons need to be further converted into some electrical signal, which is either current or voltage. Now during this conversion, some noise is added to it, which is called a read noise. So when we are reading the electrons, the noise that is added to it is called read noise. So generally for the detectors, we would again like them to be minimized. Now this slide explains the effect of spatial resolution. On the left side, you can see a low spatial resolution image. Okay, you get a synoptic view. You can see a river flowing. However, you are not able to differentiate between the roads, and you definitely are not able to see buildings and probably vehicles. But on the right hand side, you can see a high spatial resolution image where you can see even small cars. Now, this graph shows the effect of pixel size or the sensor footprint. So let's say on the bottom right, you see an image. Okay. Now this is an image which was actually on the top right as well. However, it has been sampled or it has been captured by a sensor which has very large pixel size. Or essentially, it has very less number of pixels. So let's say, for example, we consider 3 megapixel sensor. In 1 megapixel sensor, you are able to probably only make out that the first number is 2. Other than that, the other features are not differentiable. Now, if we go and sample this image by a 5.5 micron device, which is roughly 1.5 megapixel, let's say for example, you are now able to see 2 clearly. Even the horizontal and vertical bar patterns you are able to differentiate. Now, if we further sample this by image by a very small pixel, or in turn make this image a near about 5 megapixel, 5 to 6 megapixel image, we are able to see much finer details. So essentially, smaller pixel size and larger number of pixels leads to better resolution. So this is the effect of detector sampling. Now this quantum efficiency we already discussed. So let's say 10 photons are being incident on a pixel, and it is only able to generate 5 electrons. So this will be called as 50% QE. And however, on the right hand side, let's say a pixel is much more efficient in this conversion, and it is able to generate 9 electrons. So here this device will have 90% QE, which is much preferred. Now coming to a combined effect of quantum efficiency and noise together. So higher quantum efficiency leads to large amount of signal collected by the sensor. So for the same amount of light falling, we'll be able to generate more electron. And the lower detector noise will lead to higher signal to noise ratio, because signal to noise ratio is signal divided by noise. On the left hand side, you can see an image with higher noise. And on the right hand side, you can see an image of low SNR. High SNR and low SNR. You can see on the right hand side, the patterns which is there, horizontal vertical pattern depicted with number 1, you are able to recognize them on the left hand side with high SNR. However, due to much lower SNR, they are not able to be differentiated. So thus, SNR also further leads to better image understanding. Now coming to the types of detectors. In silicon detectors, we generally have two major class of detectors. One is the charge coupled detector. The other is CMOS, which is complementary metal oxide semiconductor. So in CCD, a charge collection is carried out in a pixel array. And at the end of the frame, the charge is moved from one location to other location. And finally, it is fed into an amplifier and read out of the pixel. So here, essentially what is happening is the charge has to move all the way to the output amplifier in order to be read through. However, these devices have higher dynamic range. So dynamic range means full well capacity divided by noise. So higher dynamic range means higher full well capacity and lower noise. And since we are collecting electrons directly and we are transferring them, they can be added together while transferring. Hence, we can have an electron multiplication kind of effect, which is also very similar to time delay and integration. And these detectors, they have very high performance and reliability, and they have been in operation for decades altogether. This is the prime detector of choice when it comes to scientific applications. And also looking at the longer wavelength, which is IIR, they perform better. Now coming to CMOS sensors, most of your cell phone sensors will be CMOS sensors. They collect charge in each pixel, and at the pixel level itself, the charge to voltage conversion happens. So here you need not to move charge from one location to another. You can directly read the voltage at each pixel location. So they have their own amplifier and readout multiplexer. So essentially, since we are not moving charges for which the mobility is low, we can have very high readout speed, and they are less prone to radiation effects and simple interfacing. So they have their pros and cons compared to CCDs. Now coming to multispectral imaging technique. Let's say if we want to capture multiple bands simultaneously, we resort to multispectral imaging technique. And here this example is shown, which is a multispectral CCD with multiple filters placed on top of the detectors. So we put multiple filters as seen on the right side image as well, which can select the electromagnetic band that we want to observe. And then it can be further converted into the electrons for further processing. Now, this is one of the example of advanced color imager. The cell phone sensors are basically RGB sensors. They are trying to mimic our eye response, which has rods and cons. And cons, they respond to three different colors: red, green, and blue. So the sensor generally have a bare pattern on top of them, which is like this. You can see that there is one blue pixel in every 2x2, two green pixels, and one red pixels. And they essentially form a bare mosaic pattern, which is then processed to generate a real RGB image. However, there are new techniques where we are trying to put 3 layers of different filters on top of each other and capture each band in full resolution. Now, coming to some of the scientific applications, as I discussed earlier, that generally CCDs are preferred choice, but now CMOS detectors are also catching up. They are having low and low noise performance. There are detectors available which has detector read noise of only 1 to 2 electrons, and they also have multiple gain for high dynamic range. Here this image is captured and different integration time. Integration time is the time for which we are collecting the electrons, or we are collecting the signal. So you can see that image is very clearly visible when we are collecting almost 50,000 photons. However, this device with very low noise, it is even able to generate a good quality image even with 100 photons, which generally speaking is very low. It is like a twilight kind of illumination. So even during midnight, you can be able to capture images with such sensors. Now, this is a very advanced new advancement in imaging sensor. It is called an event imaging sensor. So it is trying to mimic how the human vision works. So we actually do not capture the image continuously. We only subtract and we see the change that is happening, and only that information is fed to the brain, to the neurons, so that only small information is passed to the brain to process. So this sensor is also trying to mimic so by having a luminance change detection unit. So the pixel unit is similar to what we have normally. However, this is fed into a processing unit, which is a luminance unit, which converts the change into an event. So it can be either plus event where the signal has increased, or it can be a negative event where the signal has reduced. So you can see on the right hand side, a normal camera will produce an image like this. However, in EBS will produce image as seen in the bottom. It will only produce the location where changes has happened. So doing so, we will have very less information and we can capture images at very high rate. Now coming to IR detectors. So IR detectors, since the wavelength is very long, the band gap has to be very narrow. However, this small band gap causes a problem that even at room temperature, the electrons in the valence band are able to jump to conduction band and generate what we discussed as dark current. So generally for them, the dark current is very high. So we need to cool this detector in order to reduce the dark current, and the coolers can be passive or they can be active. Now the choice of detector material also varies based on the different wavelengths. We already discussed them, that MCT generally is the preferred choice over here, and they operate in the wide spectral region, and this is the typical cooling temperature when we are in different wavelength region. As you can see, when we are going to LWIR, longer wavelength, the band gap will further narrow down. So we need to cool the detector further. So against 150 Kelvin at SWIR, we need to cool down to 50 Kelvin. Now, if you look at the detector material, so this MCT is again is dominating the IR detector regime, and here the composition is like mercury, cadmium, and telluride. So if you look at mercury telluride and cadmium telluride, their composition is varied. Basically, mercury telluride is a semi-metal, cadmium telluride is a semiconductor. If you remember the band gap diagram, so we are trying to mix the semi-metal and a semiconductor and generate a band gap in between. So it can operate from 0.7 to 20 micron, and it has very high detectivity. However, the cost and process is very complex. Now there are discrete detectors like this. These are single pixel detectors. This is a passive cooler, and we are able to cool them. And then there are hybrid area arrays. So on the front we have an MCT array, and on the back side we have a CMOS detector. But the photodiode is not there. The photodiode is replaced by an MCT array. So the conversion happens in MCT from the radiation to electron, and from electron to further is processed by CMOS. And these are integrated detectors, they work through assembly. So these are detectors which comes with their own integrated cooler. So you can operate them in any given environment. Now coming to the final part of the presentation, which is detectors in ISRO. So these are some of the detectors. You can see this is a detector which we have flown in one of our mission, which is there for monitoring the ocean color. And it was actually developed within India, which is Semiconductor Laboratory, Chandigarh. So this was end-to-end developed within India. And then we have this is the camera used in China to capture high resolution images. So it was a 12,000 pixel elements in across direction. These are some of the detectors with multiple bands and an area array sensor that we used in our Cartosat and payloads for Mars. And these are again some of the scientific payloads like Aditya L1. This is a scientific CMOS which generates a very low electron noise. And similarly, this is a detector which works in SWIR with very low electron noise. Now, this is the indigenous development that we have taken for VNIR detector that is visible in with this act. So we have started as discussed that we have developed VNIR detector for our OCM in SCL Chandigarh. And further also, we have carried out design of these detectors, even larger format detectors with some of the fabrication in SCL and some abroad as well. Coming to the IIRS also, we have carried out indigenous development of this cooler assembly. This is a detector that we have developed in-house. The focal plane array, which is an MCT component, it was procured from outside because the process that is involved to develop them is critical and under development, however, not yet completed. So this complete development also was done within SAC, and we were able to develop a working IDCA model. That is all from my side. Hope I have finished in time, and thank you. Questions? Hriday?
Yes, sir. So there is a few questions. One question from Sudhanshu is to describe the working of CCD charge coupled device detector and why it is important. If why is it important in astronomy and space application?
Yes. So CCD, as I've already described, essentially CCD forms a PN junction, which is a P-type and N-type semiconductor. They put together, and the device is reverse biased in order to have a higher depletion region. And that in the depletion region, there is dearth or absence of charges. So when the light is falling in the depletion region, an electron hole pair is generated, and they move to the opposite side. And by either capturing the electron or capturing the hole, we can actually count that how many radiation is coming. And why it is critical in astronomy and space application is due to two factors. One is the dark current. The CCDs, they generally have very low dark current. And the other thing is their high quantum efficiency. And one more thing is also their read noise. So they generally have one output amplifier for the whole array. So the benefit of this is that you can have a well-designed amplifier of very low noise. In astronomy specifically, when you are integrating when you're capturing the images for minutes altogether, both your dark current, which is the accumulation of dark pixels over the time, and your read noise becomes very critical. So that's why CCD is the choice for such applications. There's further
Okay.
question to that.
Another question is, sir, which sensor is currently the most critical for monitoring the climate change in Indian subcontinent?
Okay, so climate change as such is a very broad measurement domain. So there are defined variables which are known as ECVs, essential climate variables. So these are various physical properties of your atmosphere, of your surface, which have to be measured, and they are generally measured by various sensors in IR and IR domain. So if we talk about the detectors that are used in such satellites, they are mostly IR, which are again based on MCT area arrays. And the sensors essentially are like imager, sounder, and gas component measuring satellites.
Okay, sir. And another question is, what are the future technology that can be integrated with the sensor technology for better performance?
Okay, so one thing that was discussed is that even when we are capturing electrons and we are converting them to charge or voltage, be it at photo site like in CMOS or at the output amplifier in CCD, still the output of the sensor is electrical signal, which is then further prone to electromagnetic interference, okay, and other degradation, which we are still facing. So one of the advancement that is required is the conversion of this electrical signal again to optical signal for further transferring in the electronic unit. So now there are devices which are coming and having a photonic ICs within them, so that the electrical signal that we have captured and converted into a digital signal can then be transferred into a fiber optic. And the other technologies that we are working on right now is hybridization, where multiple detectors like an MCT area array and then a low noise ROIC and then a processing unit, they are packaged together in an IC so as to have better performance.
And sir, last question is, what is a dark current? That you already explained, sir. And but okay, sir.
Yeah, yeah. Yeah, so dark current is already explained, and anyhow, it doesn't have merits and demerits. Dark current has to be minimized because dark current is essentially an unwanted signal. So is that all?
Okay, sir. This all.
Okay. Thank you very much.
Thank you. Thank you. Thank you, Mr. Nitesh Thapa, for providing an insightful lecture on detectors and sensors. And also our thanks to Mr. Hidey for well moderating this session. Thank you once again.
Thank
Thank
you
you.
sir, for providing the opportunity. Thank you.
The next lecture is on spectroscopy fundamentals by Dr. Mudit Srivastava, Physical Research Laboratory, Ahmedabad. We welcome you, sir, to start 2026 session. I would like to introduce the speaker. Dr. Mudit Srivastava is currently working as Associate Professor in the Astronomy and Astrophysics Division of PRM, Ahmedabad. Dr. Srivastava completed his PhD from Inter-University Center for Astronomy and Astrophysics, Pune, in 2010, with a specialization in optical astronomical instrumentation. During his PhD, he worked extensively on the back-end instrumentation for the IUCA Giravel Observatory and the instrumentation studies of ultraviolet imaging telescope, a payload on board AstroSat mission. Later, he was a postdoctoral fellow at the Leibniz Institute for Astrophysics, Potsdam, Germany. He has had a couple of years of industry experience as well. Before joining PRL in 2014, wherein he worked on the electron microscope-based instrumentation for the semiconductor industry at KLA Tencor, US multinational firm, as a system engineer. Dr. Srivastava's scientific work combines instrument development with observational astronomy. At PRL, he has mostly been working on the instrumentation development program for PRL Mount Abu Observatory. His observational interests lie in the studies of novae, symbiotic systems, and related stellar transients. With this, may I invite Dr. Srivastava to deliver the lecture.
Thank you very much, Dr. Praveen, for a very kind introduction. Am I audible well, right?
Yeah, you are very much audible.
Thank you. I'm going to share my screen and then you can tell me. Yeah, could you please confirm if you are seeing my screen?
Yes, visible. Yeah, full screen.
Full screen mode, and now I'm using a pointer also.
Right, working.
Great. Thank you. So allow me to start. Very good afternoon to all. It's wonderful to interact with you guys here. The title of my the presentation was given Spectroscopy Fundamentals. And when I was preparing this slide, I realized that actually I'll be talking about the fundamentals of spectroscopy in astronomy. Although the basics are same across the domain, whether you are working on astronomy or laboratory astrophysics, the fundamentals of spectroscopy and the instrument which we use for the to measure the spectrum would remain same. But in this lecture, I will restrict myself to the concept of spectroscopy, which are more prevalent in space sciences and astronomy, etc. And what you can see here from the picture that we do astronomy and spectroscopy from variety of methods using nighttime telescopes here at Mount Abu Observatory, or we study sun in daytime. Here you can see at Udaipur Solar Observatory, a telescope which is installed in the middle of the lake, or we build satellite. This is the picture of the AstroSat mission, which has the instrument which can do the spectroscopy in ultraviolet and X-rays and similar high energy wavelength domain. So this is what I planned for this lecture. We have got only half an hour or so. So loosely speaking, eight minutes each on each of the topics. So I'll be giving you the basics of astronomy and what do we want to understand while doing the spectroscopy in astronomy. What are the typical features of an astrophysical spectrum? As I said, that spectra are anyway the same, whether you are taking the spectrum of the star or spectrum of a sample inside your lab. Basic features would remain the same. So I'll touch that topic. We build, Dr. Praveen mentioned that I'm an instrumentation scientist. So I'll be touching some aspects of the spectrograph designs and some features, which I believe as an introductory course, you should also be aware of. And at the end, I'll show you some glimpse of our program at PRL, because we have been developing a spectroscopic instrument in a rather unique way. We do spectroscopy to determine something very, non-conventional, let me use the word, right? So I believe it's been 2 weeks since you have been attending these lectures. And you are well aware of that our Earth atmosphere blocks most of the electromagnetic radiations. It blocks gamma ray, X-ray, ultraviolet. It blocks most of the infrared spectrum. You can see it here. It's only a very narrow window invisible where the light can penetrate the atmosphere and come to us, so we can have a telescope at at the Earth's surface. Otherwise, you have to build a satellite. And then there's a huge window in radio domain where you can also observe the instrument from the coming from the distant sources, right? And for that purpose, we use telescope. But the telescope, what does it do? It captures the light, whatever the lights. Am I audible well, right? You can hear me, right? Could you please confirm, someone? No, I'm not able to hear you. In case you are mute, could you please confirm if you are able to hear me well?
Yes, sir. Audible.
Okay, great. Thank you. Thank you very much. Right. So, but having telescope alone is not sufficient because telescope can only focus the light. And then there was a lecture by Dr. Nitesh Thapa just before me where, he was talking about the various kinds of detector which you can use to store the light. So you use telescope to collect the light and detector to store the light. But once you store the light coming from the stars, what do you do? What would you do with it? Right? You want to derive science, right? You want to derive the information hidden inside that light. And for that purpose, you need to put instrument between your telescope and the detector. So in space science, in astrophysics, and astronomy, we use variety of kinds of instrument. Telescope is the simplest of one, right? Telescope is basically a device which will just focus the light at one particular point. So light which is coming from this direction on axis, what we call it's focused here. Light which is coming from off axis, it gets focused here. So telescope is a device which gather the light. And the bigger the telescope, more light it will gather. Right? It can also resolve the object, so you can see the things with more clarity. But once the telescope focuses the light, this light is to be fed into instrument before you record it on the detector. So this is a basic schematics which will give you an idea of whether the ground-based instrumentation setup or the space-based instrumentation setup. You need one thing to collect the light, which is your telescope. It is also called objective in some cases. And once the light is focused at a particular plane, what we call the focal plane, you can put various components like slit, or if it is imaging, you don't need to put a slit. And then using variety of optics here and here, you focus the light, re-image again on your detector and store this data back into your computer screen, right? So variety of kinds of instruments are there. You can have a simple camera here. Using the camera, you can take the pictures of the image in the sky. And then you study, you identify, oh, there's a star, this is exploding star, this is halo, this is shell, this is rim, and something like that. Or you choose to put some element here, which will separate the wavelength. It will give red here, blue here, or the other way around. And what you can do, you can record a spectrum. A spectrum is the separation of photons or the incoming light as per their wavelength. So this is the same spectrum which you must have seen using a simple prism, right, in the day-to-day activities. There's a similar thing which we do here in astrophysics or astronomy or space sciences as well. So if you take a detector and you start measuring how many photons are coming from this region, this region, this region, and that is the blue color. So it is having a wavelength around 4,000, 4,500 angstrom, until all the way red, which is having wavelength of 7,000, 7,500 kind of thing. So if you take a detector and run across it from here, 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 and just measure how many photons are coming and make a plot, then this feature is the same thing that, okay, at this particular wavelength, you are getting 600 photons. Here you are getting only 200 photons. Here you are getting only 250 photons and something like that. So this is the spectrum which we analyze, and it is lots of informations are hidden in this particular spectrum. So the same technique we use on the telescope, right? So why do you need a telescope? To study the distant star, because it's very unlikely that you will reach to those stars in near future. So till that time, you have to collect the radiation coming from the far, far, far distance, and you record that radiation. So what do we want to measure about the stars? You want to measure the mass, the basic parameters. How massive the star is, what is its temperature, what is its size, and how much energy this particular star is emitting per unit time. So mass, temperature, radius, luminosity, if you have a measure of some kind of idea about these quantities far away of far away stars, you can start doing the physics of these stars. But the trouble in this entire business is that you don't know the distance to those stars. Anyway, I'm not going to discuss here that how do you measure the distance. There are n number of methods using which you can estimate the distance. So once you measure the flux here at a telescope, and if you know the distance, which we know, you can calculate the luminosity of the star, how much energy this particular star is emitting per unit time. And if you start measuring this flux as a function of wavelength, as a function of lambda, that is a spectroscopy. So this measurements of luminosity coupled with a concept called black bodies. I understand the audience here is a graduate level students. So they are aware of, they should be aware of that if you heat a particular body, some kind of any object, and if it's in thermal equilibrium, it emits in a way which we call the black body. So black body gives you this particular equation, which says that if the star is emitting like a black body, which they are emitting like a black body, most of the star nearly are emitting like a black body, then you can connect its luminosity, its size, and its temperature using this equation. So if you can somehow measure any two of them, you can get to know the third one. So here the spectroscopy comes very handy because this is anyway you are measuring directly from the telescope. If somehow you can get to know the temperature of the star, then you can calculate its size, and then assuming some density, etc., you can get to know its mass also, right? So the same concept of black body says, and again, I'm not going to do the mathematics for you, that if you can somehow get to know how much this star is emitting in blue band, blue filter, and how much it is emitting in red band, or what we astronomers call V band, just by measuring these two, you say that 200 photons are coming here, 75 photons are coming in this particular wavelength, you can get to know its temperature. So I mean, I'm not deriving this mathematics, but it's a very simple way to measure the temperatures of the faraway objects, right? And it's a very low resolution kind of example of a spectroscopy where you can measure the temperature of the star by sitting here on the earth, by simply making two simple measurement and assuming that stars are following like a black body curve, right? The other challenge which we face in space science or astronomy, that stars are far away. Okay, so when you see with the telescope at such a far distance, 10 AU is the distance between Earth to Saturn, Sun to Saturn kind of thing, kind of a middle of our solar system, and 1 kiloparsec is a huge distance, right? It's a several thousand, 3,000 light years kind of thing. So at such a large distance, stars appears like a point source. So if you take a picture of the stars using our telescope, and this is a real picture of the stars which we have collected from our Mount Abu observatory, the star looks like this, right? All the stars looks like this. I mean, if you, it doesn't matter what kind of, it's a cool star, hot star, so red giant, white dwarf, there's so many kinds of stars, but all star looks like this because the stars are actually a point source, delta function kind of thing in terms of mathematics, and it is Earth atmosphere which blurs them. Okay, am I audible? Could you please confirm again?
Yes, you are audible.
Thank you. Right. So point is that once you take the picture of the star, it is impossible to tell what is there inside this blurred patch. It is a blurring caused by the Earth atmosphere. Star is somewhere hidden, very tiny thing here. So again, a spectroscopy comes very handy, because if you take the spectrum of this star, using somehow, and then you say, oh, this spectrum looks like a spectrum of a white dwarf. Just by looking at this image, you cannot tell whether it's a white dwarf or a red giant or any other kind of star. You need to take the spectrum. So look at the spectrum of this white dwarf, where it is emitting mostly in fact 4,000 angstrom, and then its flux decays as as you move along the wavelength. It is emitting very less in red, very high in blue. On the other hand, you can get this kind of a spectrum, more flux, less flux, more flux, huge bands of absorption, what we call it. And this is a typical signature of a red giant star. Or you can have a binary system also. When you put white dwarf or red giant together, that system is called symbiotic system. Then you can see that, oh, this suddenly spikes start appearing, which we call the emission line. So what kind of system which you are looking at, you need to have a spectrum of that system. And that's how the spectroscopy is amazingly powerful technique, because the information which you cannot find here, just by taking the spectrum, you can determine lots and lots of information, right? And once you have a spectrum of this blurred fuzzy thing, Like you take the spectrum looks like this. Then all of us, the people who are doing professional astrophysics, astronomy, space sciences, then we do a lots of theoretical modeling, physics, computer coding, everything. And then we'll say, oh, whatever is hidden inside this blurred patch, which you cannot resolve, must be having this kind of thing. It's expanding geometry. Something is blast has occurred, something is expanding in this direction, and something is expanding in this direction. That's how you are getting this kinds of a spectrum. So spectroscopy is also very useful to decipher the morphology of the system. Morphology means how the matter is distributed, the shape and size, etc. Right. In addition to that, this spectrum or any spectrum for that matter is a mine of information. In astrophysics, astronomy, space sciences, if you have this spectrum, then you can tell the distance to that object using some method, absorption redshift, what we call how far the objects are. You can actually say whether the system is static or there's a velocity distribution. It's a very dynamic system. Things are moving by measuring the width. You can tell about its density, whether the system is dense, depends upon if there's a more dense system, a lot more absorption would have been happening here. If it's less dense, then something like this. Or you can tell about its chemical composition, kinematics, temperatures, etc. So spectroscopy is an amazingly powerful technique. You measure the spectrum, and then when you start analyzing, by sitting here on the Earth, you can, just detect about its size, shape, temperature, chemical composition, distance, density, and whatnot. So it's an extremely powerful technique, right? But in a very nutshell, at a very simple language, any spectrum is having three parts, okay? Two parts basically. One we call the continuum. Okay, suppose you are sitting here, you can see my cursor position, right? Can somebody please confirm?
Yes.
Yeah, great, thank you. So you are sitting here observing a star. So a star itself is emitting, which we call the source, some spectrum, which we call the continuum. It's a background thing which this part is emitting, right? And if the star is a thermalized system, as I already discussed about the black body concept of black body, if the star is like a black body, this continuum will follow the black body shape. And apart from black body, there are other kind of emission mechanism. For example, free emission. There's something called free emission. So the shape will change. So the spectrum would consist of a continuum. And then once this spectrum passes through the medium, then lots of features gets added onto it. Okay. For example, if there's a huge hot gas, then this gas is emitting according to its composition. For example, if this medium is made up of hydrogen, and hydrogen had energy level, which you go from the lower level to higher level to lower level. So when the atom makes the transition from higher level to lower level, it emits light at a certain wavelength. And in the spectrum, you will see these kinds of emission lines, right? So you get an emission feature. Similarly, if there is a cold gas here sitting here, then this cold gas will absorb some wavelength along as the radiation from the star travels to you. And there you get the absorption spectrum. So in the continuum, you will see the dark patch, a dip like this. Okay. So any spectrum is made up of continuum, emission, and absorption features. So this is the picture. This is a don't worry about. I don't want to go too deep into that thing. This is the professional astronomical spectra, which we had observed with our Mount Abu telescope observatory. So you can see here that we start observing a particular star in 2019 all the way till 2020, all of 13 months kind of observations. Okay, so here you can see this continuous thing is the continuum. Right, the continuum was keep on increasing in the November 2019, keep on increasing. Suddenly it become flat. So we study that kind of thing, why the continuum of the spectrum is changing. On the continuum, you are seeing the emission line. It start appearing and disappearing. For example, this picture. And there's an emission line here, suddenly it's gone. or this particular feature. You can see it here. There was no emission line, and it appeared, and keeps on getting strengthening. Okay. Or there are absorption features, which you can see here. So a typical spectrum in space science, astronomy, and similar kind of thing you all might be seeing in your laboratory also. Okay. So a continuum, emission, and absorption. These are the three basic components of any spectrum. And this is what we measure and study them. Right. So this was about the spectroscopy. Let's come to the device or instrument with which we measure the spectrum. And this instrument is called the spectrograph. As I said, you need to have a telescope here because this telescope will focus the light. Then at this particular place, you put an opening here so that only light from the interested star will go through this. This opening is called slit. It's a rectangular piece. Okay. And this slit will, you put additional lenses here. And somewhere here, you put an element which we call a dispersive component, which break this light into its two components, red, blue, and yellow in between. And then you record a spectrum here, which you can see. This is on the detector, CCD detector. This is a star, which is a point source at the center. Its light is dispersed. So blue is here, red is here, and something like this. These bands are where the star is not there, and these are the bands of your night sky. Night sky also give you light. So star is localized here. That's why you see the spectrum like this. And sky is everywhere. So you can see the bands of sky emission. So this is the typical, layout of the spectrograph. And the most important component of a spectrograph is this quantity called dispersive element. Of course, slit is also very important because slit will decide the resolution of the, spectrograph along with this dispersive component. I'll come to that. So this dispersing element can be of various kinds. Anything which will break the lights into its spectrum, red to blue color, something like that. So typically we use 3-4 kinds of dispersive element. Prism is the most common device, which you can see here. So there are trouble with this. It's not a linear dispersion, it's a non-linear dispersion, which means spectrum is compressed here, diluted here, but it will give you a very good efficiency. Or we use a device called grating, which is basically a lots of very fine lines on the surface of the glass, ruled on the surface of the glass. So grating can also give you the spectrum. You can, you can use grating to record the spectrum. Or you can use a combination of these two, which we start calling GRISM. It's a grating plus prism. Okay. So that is also a very useful device, the combination of. So light will come here. It will first go to a prism, and then on the prism, a grating is mounted. So a GRISM is here, right? And there's something called Echelle grating. I'll talk about this in 2 slides down the line, right? There's something very special in astronomy when we go for the very high resolution. Very high resolution means 0.1 angstrom kind of thing, or maybe less than that. Then we have to use this kind of very special grating called Echelle grating. I'll talk about this. One of the most important parameter of the spectrograph or the spectrum is its resolving power, right? You can see it here. This is high resolution example of a high resolution spectrum, and you can clearly see 2 features separate out here. And then low resolution, these two will get mixed here. You see? So if you look at this, you will never know whether there is a 1 line or 2 line. For example, here, there's a 1 emission line here, which you can see it on the high resolution, which in low resolution, it is completely gone. So whether your spectrograph is capable of providing decent enough resolution or not, it depends upon your, the objectives, your science cases, and the choice of your dispersive element. Prism are typically used for the low resolution thing. Its resolution depends upon its material, because it's a change in the refractive index of the material, which will make blue here, red here. Okay. Or in terms of the grating, it depends upon how fine those grating lines are ruled. So if you are having 50 mm size is the size of the grating, and if you can rule something like 10,000 line into that, maybe 20,000 line more than that into that, it will give you one kind of resolution. If you manage to give 100,000 lines, it will give you much finer resolution. So grating resolving power of the grating depends upon the number of lines which is illuminated in your this setup, spectroscopy setup. Okay. And grating, one property of the grating is that it does not give you one spectrum, it gives you a series of spectrum. One spectrum here, which we call the first order, one spectrum here, one spectrum here. So several bands of spectra, which we call the orders. So if you want to go for the high resolution, you have to go for the higher order, and very special gratings are used for that, which we call the Echelle grating. And Echelle grating gives a trouble. It gives you much higher resolution. Most of the astronomical spectrum, a good number of them, I should not say most, but a good number of them use Echelle grating. So that's why I thought you should also be aware of this name at least. Later you can go to the internet and search about Echelle grating, Echelle spectrograph. So Echelle grating works in the higher order here. But the trouble with higher orders that they start overlapping with the neighboring orders. Okay. So your spectrum gets corrupted. So in order to separate this overlap, you use another grating, which is perpendicular to the first grating. So it's a two-grating spectrograph. I understand it's a bit complex, but I want you to learn the name only. Later you can study yourself, or during the question answer session, you can ask me. So it's a very special kind of spectrum. If you use a single grating, you can get a simple one line spectrum here, one. Okay. Blue, yellow, green, and then red here. If you use a Echelle grating, you will record two-dimensional spectrum, red till blue, again red till blue, again red till blue, and record it on the CCD. But this kind of spectroscopy require two gratings. One is called the Echelle grating, and another second grating, which we call the cross disperser grating. Okay. So it's a two grating spectrograph, which will give you very high resolution and a very complex set of spectrum. And this is typically we use in astronomy. So this is a typical about the, our concept of spectroscopy and spectrograph. Now let me give you very quickly about what we do at our observatory, which is PRL Mount Abu Observatory. At Guru Shikhar is the name of the peak where the observatory is located at Mount Abu in southern Rajasthan. So this is, this is Gujarat, Ahmedabad is here, just somewhere in this window, some 20 kilometers north of Ahmedabad. If you zoom in on Google Map, you will see a peak, which is the highest peak in Western India. Okay. So somewhere here on the top of this peak, we have set up our observatory called Mount Abu Observatory. And you can see lots of telescope is there. ISRO has also set up its telescope here. We have been operating a 1.2 meter telescope. Size of the mirror is 1.2 meter. Now 35 years or so. And very recently, few years back, we have set up a 2.5 meter telescope also. Okay. So this is the picture of the telescope. You can see it's a big structure, primary mirror here, secondary mirror is here. And on the back end, you can put your instrument or spectrograph. We use variety kind of spectrograph. For example, this is one spectrograph. You can see it's a very heavy instrument, 70 kg kind of thing, right? There's another spectrograph which we have kept in room. So light from the telescope, you can use optical fibers. Okay, and this optical fiber, you can feed light inside the spectrograph and record the spectrum. Right. Then this is the picture of our 2.5 meter telescope. And here you can see, right, an instrument is mounted on the telescope, which is also a spectrograph. So again, it's a massive instrument, 300 kg kind of thing. So spectrographs are a very complex instruments, right? So I was telling you on the very first, in the very beginning, the very first slide, that apart from chemical composition measurement, spectroscopy is used for variety of other purpose. And one purpose is the search for extrasolar planet, where we are using spectroscopy as a tool to detect or confirm the presence of the solar planets around the nearby stars or any other star. Okay. So you will first observe the star and you can see, oh, if there is a planet around here, then you can, when the planet will come in front of the star, you can see light getting down like this, right? And when it will go behind, then it will again, light will again up and then down and up and something like this. So you say that, oh, there could be a planet, and then using a very precise spectroscopy from Earth, because if the planet goes around the sun, the star would also wobble. So sometimes the star will go away from you, so redshifted, because any object is a Doppler effect. Okay, when the star is moving towards you, away from you due to the presence of the planet, it's redshifted, and when the star will again come towards you, it's a blue shifted. So if you start doing the spectroscopy and you see the features are sometimes redshifted, sometimes blue shifted, you can get to know, oh, there's a planet around the star. Okay, so this is how spectroscopy is used as a tool for the search of extrasolar planet, and there are very complex, very sophisticated spectrographs are there. We named them Paras 1 and Paras 2. They are located at Mount Abu, right? Using which we can detect planets around the star, right? Sometimes we study the exploding object. This is only the artist concept. We call them novae, or for example, in other cases, supernovae. So when this thing happens, and you can see it here in this picture this is a real picture of the sky, that on 15th of April 2015, nothing was here, but a year down the line, something has appeared here. It's some kind of explosion which brightened up. And using our spectrograph, this is another spectrograph, right? We keep on recording its spectrum, and then we'll tell you that how the spectrum is evolving, what is the cause, what was the cause of explosion, and why did it happen, something like this, right? You can see the spectral evolution, that in the beginning it looks like flat, then suddenly something has appeared. It has its meaning. So this is what the kind of job which we do with spectroscopy, right? And one of the latest application of spectroscopy is the measurement of polarization, because light has a direction, right? If you are aware of the concept of polarization, so I have a very video, you can see it here. This is my computer screen, and this is the sunglasses which I wear. Is a polarized. You might also be using it. It's a polarized sunglass. So I rotate it, and then you can see the intensity of the. I'll show you the video. Intensity of the light which is coming from the background screen, from my laptop screen, will be diminished, because light which is coming from the computer screen here is a polarized in nature. It has a direction. So when the light direction of the glass and direction of the laptop, I'll show you the video. Let's look at this. You see, just suddenly now I'm rotating the glass, and suddenly you see the complete blanket. There is no light coming from now. When you rotate it again, you can see the light coming out of that. And this is happening because light which is coming from the laptop screen is having a direction. And when the direction of the glass and direction of the light matches, light will come out of this glass. If it doesn't match, there will be complete darkening here. This property is called polarization, and the same thing happening with the star as well. The light which is coming from the star are having some direction, and we measure it as a function of lambda. So again, the spectroscopy. You can see an instrument which we built here in our lab, and later we put it on Mount Abu telescope, using which we can measure how much light is polarized for each lambda. This technique is called spectropolarimetry. So you need a spectrum, and each point of the spectrum you will be measuring the polarization. So this is a very special case of spectroscopy where you can do the polarization measurement here. And this is the last slide, of course. You can see here, this is the Echelle spectrum I was telling about. It's a very complex set of spectrum. You can see it's not a one-dimensional spectrum, it's a two-dimensional spectrum, right? And then using which you can see some emission line here, very bright emission lines. You can see the light is completely, diminished here. So the absorption lines here, bands are continuum. And using this instrument, you can measure the spectrum here, which you can see on the top panel, and polarization also. So this is one application of the spectroscopy. And I'll close here, and we'll take some questions now. Thank you.
Thank you, Dr. Mudit Srivastava. We will see some questions.
I'll stop sharing my screen.
Yeah, no issue. Let it be there also. If you want to highlight or something, you can use it. Okay.
Yeah.
Some few questions are there. So what is the difference between Stokes and anti-Stokes lines in Raman spectroscopy? Actually, this is not related to your topic, but because of the interest. Yeah.
Right. So these are actually the topics related to the polarization, because the light which comes from the various, for example, in the presence of magnetic fields or even the Raman spectroscopy, when there is some kind of external influence, whether it's a star or it's a lab, it's the same thing, right? Physical conditions are the same. So for example, magnetic field is one of the external agent. So in the stars also, when you have very strong magnetic field, you will get to know that your atomic energy levels get separate in the presence of the magnetic field, and then it will give you two distinct transition or emission lines or absorption lines. So when you do the spectroscopy, if these two different lines are present, you can infer, oh, there is some kind of external agents are present. So in the laboratory, you can talk about Stokes and anti-Stokes lines. In astronomy and astrophysics, we call it Zeeman splitting, for example. So spectroscopy is very useful, rather essential, to identify whether such things are happening or not. If there are no magnetic fields, you will only see the single line. If there's a magnetic field, and again, I'm talking in a very layman's language. So actual thing might be in the terms of the equation are very, very complex. But considering the broader audience here, I'm just explaining in a very layman's thing that if you have external agent, you can see its imprint on the spectrum in terms of the multiple absorption or maybe emission line. I'm not sure, but absorption lines are there.
Okay. The next question, how the atmosphere of our Earth and astrophysical objects affect the image detection from very distant objects? What are total corrections we use for this?
Yes. See, atmosphere of very distant object, they are so distant to us that typically they have no effect on the image quality. It is the atmosphere of the Earth which troubles us. Okay, because it is closer to your instrument, measuring instrument. So that it's a troublesome thing, and that is the reason we want to put our telescope on a site, ground-based instrument, ground-based telescope, where the atmosphere is very neat and clean and stable. And one of the reasons that most of the telescopes and observatories are located far away on the top of the hill where the atmosphere is stable, we astronomers are continuously looking for a better and better site. Of course, the best is to put your instrument or telescope or spectrometer above atmosphere. For example, space telescope, Hubble Space Telescope. India is having UV Space Telescope, for example. Okay. But for some reason, if you have to be on the ground, then there are technologies within using which you can correct the atmosphere. There are techniques for something called adaptive optics, where optics which it adapts itself as per the changes happening in the atmosphere. So there are complex imaging techniques available here on the ground, but best is to go to the place where atmosphere is not causing much trouble. Yeah.
Okay. Then next question, how does a spectral line broadening affect our ability to accurately determine physical parameters like temperature and velocity?
Yes. So see, line gets broadened because of multiple reasons. Okay, one is some reason which are intrinsic to the star. If you observe three kinds of stars, one star is giving narrow line, one star is getting broad line, and one star is getting broader line, then this is the thing which you would like to measure. Okay, so you cannot do anything. You can deduce that, oh, star is giving narrower line means it is static kind of thing, not much velocity dispersion. Star which is giving you broader line is having lot more velocity dispersion. Things are moving very fast here and there. But the second reason with which line can broaden is because you build a poor instrument. Your resolution is not good. And this is what we call the instrumental resolution. Okay. So this is what we want to minimize while designing the instrument, that, okay, I want to measure the star is giving the let's say you say in an angstrom, the star is giving the broadening of 1 angstrom. And there are n number of reasons why this broadening is happening. Maybe the star is having the star is moving fast or whatever is, you are measuring is dispersing the things at 1 angstrom level. So let's say star is having 1 angstrom level and your instrument having a resolution of 5 angstrom. So the final broadening which you will get while measuring 1 angstrom star width with 5 angstrom instrument width is something like 5 angstrom, 6 angstrom, and your results is corrupted. Okay. So you need to have a very good quality spectrometer. Before that, you need to know that, oh, my spectrometer is something like 5 angstrom. So with this, I can measure the star which are having width of 10 angstrom. With 5 angstrom resolution of width of the spectrometer, you should not try to measure the star of 1 angstrom width. So this is how the width of the measured line gets affected. Why the stars lines are having width in the very first case is the physics of the stars. There are n number of reasons: pressure broadening, temperature broadening, anything which can give you these kinds of intrinsic line broadening, what we call.
Okay. Next question is, what types of molecular internal energy are studied in different spectral regions?
Yes. That again depends upon the kind of the elements which you want to study, or whether you are studying the molecular transition or the atomic transition or the nuclear transition for that matter. So, for example, the hydrogen atom, which is the simplest of the atom and it's more prevalent in universe. The typical energy level falls in somewhere in the range from UV to optical to near infrared. Okay, so again, it's a 10 plus 2, 12th standard physics, or maybe BSc first year standard physics, atomic physics, where when the atom makes the energy transition from higher level to lower level, they emit a photon of visible energy. So it completely depends upon the kind of, for example, I'll tell you, like carbon monoxide is a very interesting and very important molecule in astrophysics, because after hydrogen, it's a CO which is very stable. Okay, but it's just the molecular band of CO or carbon monoxide, they emits mostly in near infrared, something like 24,000 angstrom and something like this. But there are elements like nitrogen, oxygen, this hydrogen, of course, helium, which emits most of its transition in UV, ultraviolet, something around 1500 angstrom, 2000, and all the way to optical and something around what we call a JHK band, 10,000 angstrom something. So it typically, most of the atomic transitions are happening in UV, optical, infrared. When you go for the other kind of, for example, spin flip transition, it happens in the radio wavelength, because the energy involved is very small, and energy is small, the frequency is small, so wavelength is very large. So those kinds of transition you study in radio. There are elements which is having extremely highly energetic. I mean, iron line, for example, it emits its photons in X-rays. So, to study those kinds of elements, you need to go to the X-ray. So basically, it depends upon what kind of element you wish to study, what kind of element which you are anticipating that in this particular star, these kinds of elements are present. So you choose your wavelength band suitably.
Okay, another interesting question. Can two different stars have identical spectra?
Can two? No, it's the other way around. If the spectra are different, then the very first question, that why are they different? Okay, so identical star, if you say they are identical, their signature should be the similar. Okay, so if we see two spectrum and those two spectra are different, so you don't know what is happening. It's only the spectra which you are having. If there are two spectra are different, then at the input there has to be something different. They cannot be point by point identical, right? Otherwise, their spectra would have been identical.
Okay, then maybe the last question. To what extent do our model assumptions affect the physical properties we derive from spectra?
A lot. So when you get the spectra, there are cases where it's a very difficult to converge on the model. There are cases where you can choose this model is also satisfying, this model is also satisfying. How to debug what we call a degeneracy. Okay, for example, if I give you a typical spectrum, the temperature of the star and gravity of the star is having gravity. Okay, these are the two parameters, and in some rare cases it can happen that gravity 1 and temperature 1 and gravity 2 and temperature 2 are giving the nearly similar kind of a spectrum. So in such cases, in order to break that degeneracy, you have to invoke the physics. That, oh, model 1 is telling the temperature of 3000 with some gravity, and model 2 is telling you the temperature of 35,000. Now 35,000 is not realistic because physics prohibits that. So you need to understand the physics, and you need to see that in case you are getting two different model, which model is more acceptable scientifically, it is not violating any laws of physics. So we come across this kind of situation very often, where we have to invoke physics, our understanding of physics of the system, to break that degeneracy.
Yeah, thank you, Dr. Mudit, for providing an informative as well as very interesting lecture on these fundamentals of spectroscopy. Thank you very much.
Thank you, sir. Thank you. It's an honor and a privilege to be here. Thank you. I'll disconnect now, sir.
Right.